So volumes are not equal to persistent volumes. Volumes bring persistency to containers to some degree. They allow sharing information with containers, but they do have a different life cycle than persistent volumes. A persistent volume, for example, doesn't die with its pod, as we will see. So we should keep in mind that the volume mount is a very broad term. So if you have a persistent volume claim and the persistent volume claim is bound with a persistent volume, you still have to use a volume mount to mount the persistent volume to your pod. Persistent volumes are different from volumes because they live longer than a pod. In particular, if your pod uses a persistent volume claim and you also have a persistent volume provisioner that will automatically create a persistent volume for you, and you delete the pod, this will not delete your persistent volume. This is good because if you accidentally delete your Postgres pod or stateful set, it will not delete your data. You can still create a new pod and bind the new stateful set with a new pod to the same persistent disk, and you'll have access to your data. But it can also be bad because if you don't garbage collect your persistent volumes, well, and you're on Amazon, or on Azure, or on Google Cloud Computer, or Ali Cloud, where you have to, obviously you always have to pay for storage somehow, but, well, you could be surprised how expensive that can get if you just forget about deleting. There are also policies that will allow you to automatically delete your persistent volumes, but in my experience, it could be the case that, for example, a persistent a stateful set with a database cluster may enter a state where you cannot recover the cluster automatically. It may be even the simplest way to destroy it and recreate it. So in this case, it would be very nice to still have the persistent volumes. So just keep in mind as a takeaway, the persistent volume has its own life cycle, and it's good. It's good for you because you have control over the life cycle, but it also comes with the responsibility to take care and garbage collect the persistent volumes when they're no longer needed. All right, so in order to use persistent volumes, we need to wrap our head around at least 4 concepts, maybe 5 or 6. Volumes, well, the generic volumes, empty dirs, config map mounts, and so on. They live and die with a container. Then we have volume mounts, which is a generic way of getting something like a volume into a container that also includes persistent disks. So we use volume mounts quite a lot. And when we think about persistent volumes specifically, then we need to understand the persistent volume is the actual disk. The persistent volume could be backed by a file system-like thing, like NFS or Elastic File System on Amazon, or it could be backed by a block device, such as EBS. So, well, I think, in my perception, using a block device that will be formatted with a file system is the most common use case for databases and data services. So think about the persistent volume as the actual thing that you'll write to. So it will show up after you've volume mounted it into your pod as an ordinary directory. But this directory is basically a remotely attached hard disk. That's the mental model. Now you would ask yourself, why can't you just take the persistent volume and put it into the into the pod specification, or into the specification of your stateful set? Well, because there is this concept of You can create it manually or you can create it automatically. That's why the persistent volume claim is there. The persistent volume is the disk itself, so at least it's representation because the disk is residing on some storage server. So the persistent volume is the representation of a persistent disk remotely attached block device, which can be created manually by an administrator or alternatively created automatically. Then you have the disk, but you have not decided at this point what to do with the disk. The what to do with the disk is answered by a persistent volume claim, which is basically some entity that can make use of a persistent volume saying, I want a persistent volume that looks like that. So the persistent volume claim is basically uttering or requesting a persistent volume of a certain quality. And then Kubernetes will look, is there a persistent volume that matches this desired specification? So this brings us to the storage provisioner. This is, I think, the official name, which can be configured as part of the so-called cloud config. So, for example, if you're using Any9's Kubernetes and you are in an Amazon environment, so we have Any9's Kubernetes running on Amazon, for example, among other infrastructure providers, then you could configure a provisioner that will, upon request, provision a EBS volume, an elastic block storage volume, dynamically. So your stateful set creates a persistent volume claim. The persistent volume claim will be observed. There's a new persistent volume claim. Do we have such a volume? No. So let's provision one. Now we have provisioned one. Let's bind this persistent volume to the persistent volume claim. This is how it works. So there's another concept called the storage class, which allows you to, let's say, extract the quality of the persistent disk you want to have in a persistent volume claim into a reusable entity. So it's pretty similar to what you do in modeling a relational database schema. Let's say you have a list of people and they have addresses. So you could have a home address and you could have a working address. So you create that address into a separate table and then you're using joins to merge them. A storage class is basically a configuration of a storage class, and a persistent volume claim will then refer to a storage class to specify what kind of disk you want. So while the persistent volume claim has knowledge about or describes how big the disk should be, the storage class could, for example, describe, do you want an SSD disk, or do you want a hard disk, or do you want a fast SSD disk? So if there are different types of physical disks available in the cloud config, like it is in the case of Amazon cloud config, then you can use the storage class to address those different disk types. So, for example, if you want to have a database that produces a lot of data, and you care about cheap storage, you don't care so much about performance, then maybe a physical disk is the better choice. If you want something that's very, very blazingly fast, then you want to go for an SSD or a particular flavor of an SSD. All right, so as I said, the persistent volume claims is the demand, describes the demand for the persistent volume. In a stateful set, you will also have, as a part of the stateful set definition, a persistent volume claim section. Once the persistent volume is created, you will use a persistent volume mount to mount the persistent volume into your each container. Be aware that mounting a persistent volume into or using a persistent volume with multiple processes may cause problems, like accessing a file on a file system could cause different problems. EBS block devices, for example, have the speciality that you cannot create an EBS volume, a persistent disk, and then mount it into several VMs. So you cannot mount one particular persistent volume, in this case, into several pods. At least that's not a good idea in most of the cases, and it might not be even possible. We'll look into the way stateful sets are structured in greater detail throughout the session. So don't be afraid if you don't get all this load of information right away. So the persistent volume claims basically says, give me 3 gigabytes of fast SSD storage, and this fast SSD storage is the quality that is described by the service class, storage class. So it's not a complicated thing. We'll see examples, and it describes the quality of the disk, among other information it may carry. The storage provisioner, as I said, is the agent that will monitor persistent volume claims and create persistent volumes on demand. There are several different providers, adapters, so to say, that will allow you integration of existing storage solutions, from software-defined storages to infrastructure provider specific solutions. So you'll have a variety of choices, regardless of whether you are in an on-premise scenario such as your own data center, or whether you are using a public infrastructure provider such as Amazon, Azure, Google Cloud Compute, or AliCloud, or whatever, DigitalOcean. There's so many of them. I also said you can do manual provisioning, but I mean it's 2020. If you don't get a provisioner up and running, so maybe you shouldn't operate your own Kubernetes cluster. I know it's a strong opinion, but I'm a huge fan of on-demand provisioning of data services. So a Kubernetes cluster without dynamic provisioning of persistent volumes would be useless in my experience of Kubernetes, but might be different for you.